Welcome to Demystifying Delta Parquet. My name is Jarid McKenzie. I'm an analytics architect. Basically, if it involves enterprise analytics or understanding the state of your organization, I've done it. From reporting to data engineering to architecture to business analysis, I have basically swam the full gamut of what exists within analytics. A little bit about myself. I've actually recently become an independent consultant, so I'm doing some consulting work myself right now. I spent the last 6 years as the lead analytics architect of a consultancy here in Calgary, Alberta. Iteration Insights, wonderful organization. If anybody is looking to reach out for help on data and analytics. I've taught this type of information at a couple of different post-secondary institutions, notably the University of Calgary and SAIT, which is the Southern Alberta Institute of Technology, more of a technical school here in town, doing business intelligence-like activities. You can find me on LinkedIn there. My handle is Jarid-McKenzie. I do have a website, although it's not very active, foundatum.ca. And you can actually look at my GitHub site, also Foundatum. Couple things that are on there that I think are really useful. This presentation is on there, so you're more than welcome to grab everything in here. Also, the live demo that I'm going to be doing towards the end is all scripted on there as a Python notebook, so you will definitely have access to execute everything that I'm doing here and see how everything works on your own machines or within your own environments. And lastly, I am an all-around nerd. If you find it nerdy, I probably do it. You'll notice my presentation's a little bit of an 8-bit theme here because I like that kind of thing. And I'm also a D&D aficionado. You can see a bunch of D&D books back there. So you'll see that that's kind of a running theme through lots of what I end up talking about. Okay, let's get started. This presentation is kind of broken into 3 different parts. The first section here, we're going to be talking about Parquet files because they're really the foundation for what you actually need to do with Delta and Lakehouses and these types of environments. The second part will be talking about Delta. So what does Delta do on top of Parquet files? And then we're going to go through a demo and see what the implications of all of these types of things are. All right. So if anybody goes to the Apache Parquet documentation, it is really challenging to understand. It takes a long time to actually decipher what has been put in there. And it's what I've got as a quote on here is really just describing the process. And it doesn't really just tell you what you can do, what you should do with Parquet files, and more importantly, what you shouldn't do with them. So it's one of those things where I tend to find it's not very easy to actually get good guidance from the documentation, unfortunately. That's why I've kind of gone through as much as I possibly can and distilled it down to a couple of points that I think are incredibly important for folks to understand and actually implement on their own. So one of the first things is that although you can use Delta Parquet to do transactional-like operations, you probably want to be very careful with how it's actually being implemented. Oftentimes, transactions allow people to say, oh, hey, I can just implement this like I would any OLTP database. So we're going to go into why that is, what the implications are of what's going on here. So Let's talk about a little bit of relevant background. So this is all about how data has been stored in the past traditionally. I'll mostly be using SQL Server as reference because that's what my background typically has been in. I've been, doing this type of stuff for about 12 years now, and I've just kind of transitioned from SQL version up to the cloud and doing data and analytics. So uh, first one is for row order. When you look at a data set, if you look at the actual bits and bytes that are in a page file, you'll find that the data for one record is stored one next to the other. Now, this is really good and really useful for the use case that we're doing it in of an OLTP database. Remember, that means it's a transaction processing database. So what's the goal of these types of things? We're creating new records. Usually when you create a record, you're inserting each and every one of the fields at that moment in time. We're reading a record, so I want to retrieve all the information associated with one record that I want to do some sort of work with. So I need to go out to the database. Database goes and reads its underlying files and returns all that data back to me when I need it. So the actual read operation that happens, it goes, gets one row, and returns that one row. So to make that efficient, it just reads memory, or it reads disk at that point, loads it into memory, and then passes it back to the end user. But it's all about minimizing that sort of operation. I often find when people are doing either transactional processing or analytics processing, which we'll get to in a second, they forget what's actually going on in the machine. You need to go out to a disk, load that into memory, and then give it to the user who is actually looking for. Doesn't matter if this is on the cloud, doesn't matter if it's somebody else's computer, it still has to happen in that sort of way. What's nice about transactional processing is the use case that you're developing this for allows for a significant number of readers and writers doing those very small transactions, or ideally small transactions at that moment in time. So they can just write bits and pieces of the data without locking everybody else out from the system. It's making the right tool for the job that you're doing at that point in time. Let's contrast that with column order, which is, again, that's generally for analytical processing databases. And those are stored with all the data of a single column, one after the other, on the disk and then in memory. The point of this is so that we can have really high data compression ratios. We can do very fast filtering and fast aggregations. This is also generally good for those larger transactions that tend to take place. So what you would be doing with something like this is I'm going out and saying, give me all the products that were sold in Belgium and tell me the actual cost of those products over the past year. So I'm doing a couple of different filters and I'm aggregating. Those are the types of questions that these databases are geared towards. If you go and ask a database, hey, give me all the information associated with this one record, yes, it can do it. But that type of situation is going to require a lot more reads on the disk, a lot more memory I/O. There's tends to be a lot more operations that need to happen in the background than what the user tends to see. So really important to understand the use cases of those scenarios. We'll end up talking about this a little bit later on as well, but columnar databases is exactly what Power BI is geared towards. It's also what Parquet files are built upon. So Parquet, going back to Parquet with that as our basis, is a columnar file format. I'm not going to say it's a database because, as we'll see in a second, the Parquet files themselves are written once. So that's going to have some implications. What is different about Parquet in this instance is that it actually extends that columnar idea as well. And it allows us to do some nesting of our columns. We can store many rows within a row. I know that might not make a ton of sense right now, but we're going to take a look at that in a second. But it's important to know that these are particularly columnar files. All the data associated with one column is stored one after the other in the actual file itself. So where does this actually get its name from? Parquet actually comes from parquet flooring. You can see some of the things I've got on the screen. There's different styles of parquet, but in particular, there's lots of different columns that are stored one next to the other, and the data is not interspersed between one another. So columns are stored by themselves. There's some default sizes that are important to know and understand. Row groups, we'll get into what a row group is in a second. Basically, it is a set of rows. So I know I said all the columns are stored one next to the other. It's yes, kind of, mostly. So there is a row group. It's basically give me a gig of data, which is what the default size for the row group is, and then we're going to store a columnar format within there. Each of the columns within that group stored as a column. They're written as data pages, which are 8 kilobytes. These are the same kind of thing that you'd see on a SQL server with their 8K pages. Metadata is actually stored at the bottom of the file. So when these types of files are actually written, everything is stored in a row group, and then you might have another row group, and then once all the row groups that you're storing within that one file are written, you store all the metadata at the end. Metadata is like statistics. There's some interesting filters that we're going to take a look at. There's encoding and encryption information that's stored in there. There's pointers to different parts of the file so that when the Parquet file is actually read, you can just say, oh, give me this part of the file, and there's a pointer to the start, and you just read from there. And lastly, and most importantly to understand for most of our use cases, is that files are meant to be immutable. Once you've written a file, it never changes. And some of you guys might be thinking, well, how does Delta add on top of that? Don't worry, we're getting there. All right, let's go into Parquet order. So just as I was showing the columnar order and the row order, the big one I want to show here is just a very similar visualization of how data gets stored. So we have row groups that get stored, and then there's a bunch of statistics that are in there. All these are stored in order, but within the row groups themselves, you have the columnar format. So it's just important to know that all the data for one row group is stored once next to the other. It has very similar goals to columnar data sources. Same kind of thing. We have fast filtering and aggregations, but it expands on this with it gives us a nested data structure. It is immutable, like I mentioned before. This is the goal of the immutability was originally due to the ideas of functional programming, where you have immutable data sets or immutable objects. And when you need to do some sort of modification, you basically write a whole new object. This is really useful for those concurrent reads because we have guarantees that the underlying file itself doesn't change. Anybody can read it at the same time. So when these are on our data lakes, so whether that's in a Fabric data lake or it's an Azure data lake Gen 2, these types of things can have many, many readers. And because there's guarantees that the file doesn't change, people can read it without issue. It also has really good data compression. When we have row groups of that 1 gig size, it tends to create an instance where everything gets compressed quite heavily. And we're going to talk about some of the reasons or the ways that it gets compressed as well.
Jared, we have a first question coming in.
Absolutely. Let's go.
I first wanted to answer it myself, but I was like, no, don't do it. So, and already somebody is going to answer it. But hey, for the question for you as well, what does Parquet order has to do with V ordering?
Absolutely. So Parquet ordering and V ordering are related, but V ordering, now, this is my intuition. This is not something I know from behind the scenes or in chats with anybody else. But from my understanding, this is essentially the same algorithms that were put in place on Power BI and analysis services and technically the Excel data model, where the way you get highly compressed and highly efficient data is by ordering the columns in a particular way. So V ordering, as Sebastian actually says in the chat there, it is a write time optimization. But what it does is it specifies the order in which columns are sorted. When I go into compression in a second here, we're actually going to see why that's the order that you store column or rows in will make a very large difference to how data gets compressed. So I'll go more into it specifically, but it's the compression algorithms that were used for the Power BI backend databases that get created and analysis services. All right. So what I've got on the screen here, this is more just an example of how the data gets stored on disk if I, without writing physical bits themselves. For example, here we've got our row, and I apologize for my chicken scratch writing, and tend to write very neatly because I'm a typer, not a writer. All the data that's associated with one row gets stored one after the other. And you can kind of see that in here. This is how CSVs are written. This is how transactional processing systems are typically written. And some of those can have other compression algorithms put on top of them, but it's stored in this row order. Other file formats that use this would be ORC, ORC. That's another Apache project that use this type of thing. Second one, in the column order, it's basically all the data that's associated with one column is stored one after the other. Same kind of thing here with all the phone numbers, names, so on and so forth. And lastly, on the Parquet side, what I'm just trying to demonstrate is that we break out our two row groups in there, and then we have our statistics. And within each one of these is a columnar format. So I know I'm putting a bunch of chicken scratch on the screen here, but the point of it is that we're using column order and row order in order to get kind of the best of both worlds, if you will. Get rid of the ink because I don't need to save that. Data types. Data types are very, very important. And that actually means that this type of thing is extendable. Most of the data types that we're using ourselves, we're never going to be creating data types within most of our scenarios. It's been built out for us. The primitive data types, what you see on the left-hand side there, we have Boolean, which is a 1-bit value. Important to note that is 1 bit, not 1 byte. So it's just a true false type scenario, allows for very tight compression. So if you're having those true false values, try not to write the word true or false. And then when you could actually use a Boolean type instead. We also have various integers of various sizes. So having the correct size integer can allow you to have more efficient compression, so that your files are smaller. You are spending less money on storage. Always a good thing to have. You have a couple of different floating point numbers depending on what sort of precision you need. So either 32 or 64-bit floating point values. And then there's two different types of byte arrays. You can have arbitrary long byte arrays, which you can think about as our string values. These are, if I have a long text field that needs to be in my data set for some reason, it's going to be stored as a byte array. We never will actually say, oh, give me a column that is a byte array, and then you're putting it on there. No, we're probably just going to create a varchar or a string type within the table definitions themselves, and it's taken care of for you on the back end. You don't have to worry about doing anything like that. It's just important for knowing. Another one that's really useful are fixed length byte arrays. This is a really useful idea when you want to do some more complex or more, it's really just more complicated types of analysis. There's a really good use case for, say, growth economics. If you're trying to see, when was my user last active within the system, or what, given the last 30 days, give me the days that user was active. There's really good efficient compression methods to use for using fixed length byte arrays. There's also a ton of additional logical types. I mentioned strings already, but there's dates, which is essentially just another type of integer. Times kind of just do a floating point number because you have the integer part, and then after the decimal ends up being the time part. And then there's a couple of other ones that really just extend these, more just different types of strings. But for the most part, most people don't need anything beyond that when they're talking about data and analytics and building out lakehouses themselves. All right, so let's do a very brief aside about nested data. You'll see my little Matryoshka doll fighting my knights there. Nested data is basically if you want to store header detail rows or a header detail pattern. Most people that have done something like Power BI or data and analytics are probably fairly familiar with the idea of a header detail record. There's actually a very good video that the folks over at SQL BI did. So I want to say it was Marco Russo or Alberto. Actually, no, I'm pretty sure it was Alberto Ferrari. Who talked about whether you normalize or denormalize a header detail table within a tool like Power BI. And I'll not bury the lead. He basically says always denormalize your details onto your header table. But within something like a Parquet file, you don't have to. The challenge is that Power BI cannot read nested data types. So at this point, I wouldn't recommend using them for Lakehouse tables. It's very useful if you're trying to do something like archiving your data. If you need to say, take all the data that's older than 5 years old or something, and take that and put it into some sort of cold storage, that's really useful use case for nesting the data because it actually reduces the repetition within your data. Again, I want to say I was doing some testing on this, and I got about a 10% more efficient data storage when I denormalized my header onto my denormalized my detail rows onto my header versus nesting the columns. Nesting gave me about a 10% size advantage, but Power BI cannot read those files. So at this point, I wouldn't worry about them for the most part. I've also got some links to the Dremel paper that this was originally based off. You don't need to understand any of that, and it's complicated, and I couldn't really understand what they were trying to talk about in there, because I didn't feel like spending too much time actually deciphering it. So let's talk a little bit about compression and encoding, because I find these tend to be some of the most important pieces to understand when it comes to knowing how the data is stored and what it actually implies. And we will end up kind of brushing on that V ordering idea that we had before. So compression, this is your pretty standard compression algorithms that are out there. There's the Snappy protocol. I want to say that was built by Google many, many years ago. There's gzip that's been around forever. There's a couple of different other ones. I have never changed my compression algorithm, especially on Fabric. Everything compresses to Snappy as default. And I have never changed that setting, so it's more something to know about than really something to play around with. You know, maybe if you're doing some archiving purposes, you could go in and play around with that. But like I said, I haven't done it, and I don't really see a need to at this point in time. What is important is that a lot of the information about the compression gets stored within the footer. So information about what the file size is when it's compressed versus uncompressed, what the codec is that's being used to do that, pointers to the start of the actual compressed column. That kind of information is all stored within the footer. So it's more important to know that that type of thing is actually in there. What is very important to start understanding is the idea of encoding. And this is not encryption, this is encoding. This is encoding is when we are changing how the bits actually appear on disk in order to achieve tighter compression or more compression. We're going to talk about a couple of these ones. I'm going to describe 4 different encodings that are useful for us. There are a couple of others, but I find that they are more esoteric and you don't tend to use them all that much. Again, you won't actually have to implement any of this. This is done for you by the underlying engines. But it is important to know that the way you show your data or the way you store your data has implications on how these encodings can be applied. So I've actually taken a couple of these screenshots from there's Microsoft documentation on the Vertipack engine, which is from Power BI and the Excel data model and analysis services. But all of that is very applicable to what we're talking in here. So the first ones that we're talking about is dictionary encoding. So on the left, let's get my pen out here. If I can not hit my screen for a second, you can see on the left, we've got a column of text values. There's just 4 different values in there: red, white, black, and blue. And if I were to store this all one after another in a column format, it would be rather inefficient because, storing the characters for red and then the characters for red again and white and black ends up using a lot of space that doesn't necessarily have to, especially when I have these low cardinality columns. So you can see on the right-hand side, this is a dictionary. It gives me an ID value of 0, 1, 2, or 3, and then the actual color. So it's kind of like a hash map if anybody's more familiar with that sort of concept. I look up the number 0, and it returns the word red. That's basically it. And then all I have to actually store is a big, long series of bits with the ID that you're interested in at that point in time. All right, sorry, I'm just seeing a couple things in the chat. Oh, perfect. Somebody put the header detail. Thank you, Oliver. That's really, really useful. All right, so dictionary encoding. It's pretty easy. It's a hash map. Run length encoding tends to get a little bit more complicated, but it allows for very efficient compression. So you'll see we've got the value Q1 stored 310 times, and then the value Q2 stored 290 times. And this could actually go on a number of different in a number of different ways, and there can be repetition in there as well. So the quarter could repeat. So you could have, for example, I've got 310 Q1s, then there's 290 Q2s. You know, maybe Q3 goes on for, I don't know, 300 instances, and then Q4 goes on for another 300. And again, apologies for my chicken scratch writing. But you could then repeat and say, oh, Q1 repeats again for another 310 records. That's absolutely perfectly fine in this. You can have repetition. It's not a primary key of the underlying table. It's how the data gets stored. Because again, looking at the left-hand side, we have a big column of data, and if I were to store all the values one after another, I would get, you know, what's this? Imagine it's a 2-character field. That's going to be what, 16 bytes? And then if I store that 210 times, I have 16 bytes times 210. Significantly smaller than if I just stored this row right here. Q1 starts at row 1 and then goes for 310 rows. Tends to be how this type of thing works. Just getting rid of my ink on the paper there. This also, do I have a page where these actually get put together? The dictionary encoding and run length encoding. So this column right here ends up getting stored as a dictionary. And then the values that we're starting and how many are being applied get stored in here. So if you put run length encoding and dictionary encoding together, it ends up being highly, highly efficient for this purpose. Again, remember, we're trying to make sure that we have fast filtering and fast aggregations. That's primarily what this is meant to do. All right, let's talk about bit packing encoding. This one, we're starting to get a little more back into the comp sci world. So if anybody remembers going back into their computer science days, it can be a little bit of a jaunt down memory lane, if you will. So right now, we've got all the values 0 through 7. These are all octets, if you will. And they can be stored with 3 bits. Typically, if you were to store these as an integer, and especially in a Parquet file, the smallest integer that we have is going to be that 32-bit integer. So if I were to store the number 1, I'm going to have 0 a bunch of times, and then it's going to be 0, 1. All of this is just repeated data. There's so much wasted space because I've stored this as an integer, which is not necessarily the most efficient data type that I could possibly do. So let me get rid of that first for now. So what's stored on here is, if I were to store all of these numbers 0, 1, 2, 3, all the way up to 7, one after another, I could pack this down into 3 bytes of data. And you'll see the number 0, if I were to show it in bits, would be 0, 0, 0. If I label the bits as ABC, you'll see those right here. Those get translated down into a bit packing scheme of right here, ABC. The next one, being DEF, gets stored DEF. So you have 1 byte of data. We've got 2 kind of values that we're showing in there. And then on the next one, when we go to the second number there, or the number 2, we have G, which is part of the second byte that's stored on data, and then HI. Now, the ordering for this is a little weird. If people aren't familiar with specific endian types, don't worry about it right now. Again, this is done for you. All of this kind of leads back to the point of the lower the cardinality of your column, the more efficient your storage is going to be. So bit packing and run length encoding and dictionary encoding all rely on having relatively low cardinality columns. There's little variation within those columns. When you get to things like those big long string columns, so say I'm doing analysis on a sales system and I have a user that puts in notes for the comments of a sales order that they're doing. Those notes, while they can be useful, are almost impossible to compress, and they are very, very different from sales order to sales order. So it tends to lead for almost no compression that can be done on those types of columns, which is why there's a general push for end users to take those types of information and say, we're just going to take that out of the analysis system. And if a user needs that type of thing, we're going to write a report that'll go back to the operational system and says, oh, give me the information associated with this sales order. And it'll go and look up all that information. Again, that's what those are for. Those types of databases are for looking up all the information associated with one sales order. So I can just do select star, bad habits, but yeah, select star from sales order where the ID equals this. You're absolutely going to store the ID columns within your analytical systems, but you don't necessarily need the comments in there always. And I know there's going to be, business users that push back on me and say, I want this, I want everything everywhere all at once, and it tends to be challenging to break that apart. But so it goes. There's a trade-off on whatever you do in these scenarios. So last one that I'm going to talk about here is delta encoding. Now, this one is probably going to take a little bit more effort to draw out. So forgive me here if I just go, if I'm not looking at my camera and rather down at my tablet here, because it is a little bit more useful for drawing. Delta encoding is all about describing the differences between values. So let's imagine that we had a sequence of numbers that looked like this. There's a 7, 5, 3, 1, 2, 3, 4, 5, right? It's a meaningless sequence. This is just more to show folks what the point of this is. Delta encoding is where we take the differences between values. So we always need to store the starting value. So we're going to store, so we're going to say, here's our start equals 7. And then from there, we're going to look at the differences between values. So we've got -2, -2, -2, 1, 1, 1, 1. So that is the sequence that I could use to regenerate my original sequence, knowing the starting value. In order for this to be, again, more efficient, we also subtract whatever the minimum value from this is. So we're going to say, we're also going to store the min value, which is equal to -2. And then subtracting this, you'll see what ends up happening. We have 0, 0, 0, 3, 3, 3, 3. What's important about this is these are all positive integers now. Important thing about that is I can save 1 bit on the actual size of my my data set, or the columns, because I don't need that first bit to determine whether it's a positive or negative value. I guarantee that this is a positive number. Then we do the same bit packing and encoding that we had from before. So if we were to take all this information, I have that start as a 7, I have a minimum value of -2, and I bit pack it. This is what those bits end up looking like. 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1. So all of this, which again would was 32. If those were 32 bit integers, that's what, 32 times 8. Can't do that math in my head off the top of my head, but you can understand we could store that as one 32-bit integer here, a second 32-bit integer here, and then a stream of bytes. So rather than this is essentially half the size, more than half the size of what I originally needed to store. There's some additional details that go under the covers, but for just eight numbers, it's actually very efficient in that regard. Let me get rid of this and show you a more complicated example that it would take me way too long to write out, but this is useful. Imagine I had a series of Unix timestamps, or even just timestamps in general. And those so I had maybe an IoT device that is constantly shooting events into my system. Each one of these could then, this is actually larger than a 32-bit integer. Typically that ends up being a 64-bit integer. So 64 times 8, again, do the math. You can see that's a lot of information that needs to be stored. I am able to compress that down into, here's the first value, here is the minimum value, and then here is what? I think there's 70 bits in that stream of data. Like, it is so efficient to do this type of thing, and it's often used in exactly this scenario where we have timestamps or numbers that are coming one after another. So again, you don't have to implement any of this, but it's important to know that this type of thing gets done on your data when it gets stored. So
Jared,
yes, go for it.
We have a question, and actually it's a very good one, in all fairness. The
right.
decoding process, isn't that very resource intensive?
It could be. The big thing is that the underlying the backend algorithms are actually more interested in answering the questions that you have rather than the decoding process. So as an example, a lot of the time these are used in the case where I have, give me all the events from this date to that date. Knowing the information that I have in here ends up being really useful for filtering the data. So I could just filter down to, ideally, an underlying Parquet file is going to filter these rows sort these rows in order of this Unix timestamp, and then it's going to find the specific rows that are going to be associated with whatever that first value is, and then it'll return value. So it's actually rather efficient for finding the specific values that you want, and then it only decodes a small portion of the underlying data. It's not decoding the entire data set for the most part with the questions that we're asking for. Does that make sense? Does that kind of address the question a little bit? Yeah, exactly. Robin made a really good comment in the chat there. I expect it to be more efficient than reading more data from disk or cache. Absolutely. All this stuff ends up being cached, and then once it's determined that we need the information, the specific information that's in those rows, then it goes through that decryption process, or de-encoding process, I should say.
There is another question coming in as well. So
Absolutely.
Delta files just take record of the differences between files. Are they kept above Parquet?
So yes, and I will be going into that in just a moment here. So you're jumping ahead on me, but this is excellent. All right, so let's talk a little bit about the Parquet footer. There's not too much that we need to understand. It's mostly the idea that we're storing pointers to different parts of the Parquet file. It stores offsets, compression algorithms, and that type of thing. It also stores metadata like the min and max values of columns. That's really useful because if you have values that are stored within different row groups, I could skip an entire row group, not have to read this gig of data into memory, and just read the next one because I've filtered out the data based off of some of that metadata in the statistics. One really useful piece of information that is stored in the footer is the idea of a Bloom filter. I love this concept. And it is the idea of a Bloom filter is that it is a very compact data structure that allows us to respond with membership queries of either definitely no, your data is not in there, or probably yes, or it might be there. And the way it ends up working is based off some hashing algorithms and then setting the bits within a certain bit length. You can imagine this as, say I had a column that had a bunch of different products in there, and they were all numbers. If I wanted to query product 1, 2, 3, 4, that 1, 2, 3, 4 goes through a specific hash. The hash algorithm returns a series of bits, and then those bits get set on the actual Bloom filter itself. So if I were to say, give me 1, 2, 3, 4, that has those specific bits, I know those are set, so I'm going to actually return, so I think it's in my data set. If we had 1, 2, 4, and miss the hash, basically you're going to have a one of those bits not set within the Bloom filter, which is where we get into this phase in here. So it's going to say, do you have this key? The filter is going to say, no, that key is not within this specific data set. Either go to the next row group or go to the next Parquet file, but it's not in here. You don't have to read this data set to answer the question you're asking at that point in time. Or it's going to answer, yes, we have it. And then it goes, reads the disk, and returns all the data associated with that specific key. Or you can have false positives. This is kind of the instance where the filter says that the data exists, but that's more just an artifact of the hashing algorithm. When it actually goes to storage, it does read the data, and it returns, oh, sorry, you've done work unnecessarily. It's not actually in there. So I always find this a fascinating concept and a really useful thing. So it's more just know that this happens behind the scenes for you.
There is a question coming in about the Bloom filter.
Absolutely. All right, let's
so
see.
It would check each and every file for Bloom filter in the footer, or have we another metadata file? I would say for Bloom filtering.
So just one quick correction: it doesn't check every file. It checks every value in that column if it's in the Bloom filter. So I can do very specific queries against my my underlying data set and say, is this value even in the data set? So should you do any sort of querying? Should I read this this file at all onto disk rather than just reading the metadata? Very efficient in that regard. All right. Does that answer your question? All right. Let's go talking about Delta. So Delta on top of Parquet. So let's address the hype that was put on top of Delta Parquet files. You know, the whole idea is that we have ACID transactions, or it has ACID compliance within the data set. That stands for atomicity, which means that all the parts of an operation within a transaction are either completely completed successfully or completely rolled back. Everything fails or nothing, or everything succeeds or everything fails. There's consistency. So this is kind of the guarantee that that a transaction will be from one state to the next. Isolation means that, you know, if other people are doing things at the same time, how do we actually handle isolating different people's changes at one point in time? And lastly, durability. If something happens to my underlying system, say the power cuts out, say, or somebody unplugs my computer for one reason or another, it ensures that it fails successfully, if you will, or it's written. Most of the time, it just fails and says that transaction did not execute. We're going to have to deal with it. The issue is that the way ACID is implemented happens in one of two very specific ways. Typically, there's pessimistic concurrency and optimistic concurrency. Pessimistic concurrency is where we are actually addressing this within transactional processing systems. Pessimistic just means that what am I assuming is the default behavior? So pessimistic assumes that there's going to be conflicts in my transactions. Lots of people are reading and writing data at the same time. So because that's the default, if you will, plan for it and address it. It locks the specific rows, and you guys may know about the lock escalation that happens within SQL Server. It manages conflicts by saying that because data is locked, you can't have conflicts, or if there is a conflict, it's going to actually fail your one person's transaction. The performance can be slower if you're doing larger transactions, but when you're doing those small transactions, tends to be blazing fast. Acquiring and releasing locks may slow things down a little bit, but it's generally not that big of a deal within most transactional processing systems. Again, as you guys have heard me say, this is ideal for those write-heavy applications where you have many users writing data into a specific system. On the other side, let's talk about optimistic concurrency. This is for the assumption that conflicts are rare. People don't generally have to worry too much about conflicts between those transactions. So what this means is that all the work that needs to be done within a transaction is completed, and then it checks whether there was a conflict or whether another transaction happened prior to writing. So it writes the data, checks whether that happens, and then saves that the data is actually taking place. The last thing it does is record that a transaction has taken place. So if a conflict is detected, if two people do write data to the underlying Parquet file, it ends up rolling back one person. This means that a lot of work has taken place that needs to be rolled back or undone. So if I have two people that are writing transactions at one point in time, and what we'll see when I go into the live demo here, is that I'm writing an entire Parquet file that was supposed to replace this, and I then found out that there was a conflict, so it throws away the Parquet file that I've written, which you could think of as wasted work or wasted use of the resources that we did. So we're assuming that that happens very rarely, but we do have guarantees that it does happen. Again, this is really, really useful for exactly what we're talking about within an analytical processing engine, because generally these types of files are not written very often, and it avoids the overhead of locking the underlying files. Again, lots of people can be reading the underlying file. It's just that we're writing it very infrequently or very sparsely. All right. There's one link that I want to put in the chat, because there's actually a really useful thing on time travel. So I'm just going to put that in the chat here momentarily. Apparently, I didn't store this as a link. I'll search that after I'm done and just toss this into the chat. Actually, I'll toss. This is a SQL Server Central link. I'm going to put it in the chat. You all can Google it whenever you get a chance. Oh no, it is a link. Okay, never mind. All right, let's go on to Fabric, where we can actually address some of these things. So I'm going to put Fabric up here. We're going to go back to the top of this file. I'm not going to execute the drop everything, because some of this stuff could be a little bit, take a little bit of time. while this is taking place, I'm just going to execute this select statement because it needs to start up the underlying Spark cluster. So you'll forgive me if that is just taking a second to start, but we've got other things we can talk about here. So ignoring this cell up here, because this is just to reset everything that I'm doing. The first cell that we tend to execute is going to be our create statement. So we're creating a table. What does that actually do? In terms of Parquet files, nothing. It does absolutely nothing when we create a Parquet file or when we create a table in terms of Parquet files. Delta tables, it actually stores the Delta, this information in the Delta log. So let's explore some of the things that happen within the Delta log there. So this is the original transaction 0. I like looking at the files that tend to get created in Delta tables because they say a lot of information about what actually takes place in here. Some of this is important to know. Some of it's more fluff about, what actually took place, the engine, is this serializable, that kind of stuff. Most of the time, you don't have to worry about these types of things. It's important to know we have the operation. I'm just going to double check my zoom it is on. Okay, perfect. When I zoom in, does it actually zoom in for you guys online? I just want to make sure that.
Yep.
Okay, perfect. Lovely. So this is the 0th transaction. So the very first transaction that took place in here is this create table statement. There's some information about the Spark engine that took place, and more importantly, on create table statements, there's a bunch of metadata that gets stored. We've got some format information. Yes, this is Parquet, V ordering. This is only available on Fabric instances. But right here, the schema string. This is really, really important because this is how the engine knows what the schema of the file is without having to read the file itself. So it goes in, gets some information about what the metadata string looks like, and then actually returns that information to the user so that they can know whether the columns that they're selecting for are there and the data types that they're doing are the data types that they say those columns are. So that's kind of the initial create statement that takes place. All right. Second transaction that I did was this insert statement right here. So you see, I just inserted into dim customer. I've got a couple of values in here. I've got myself, I've got Mike Martinez in there. That's it. So going back to my Delta log, that's going to be this first transaction right here. And if we look at the actual information that's in here, we've got this as a write operation. So you see write operation right there. The way that this, because this is an insert, you can actually append rows to your data set. We're going to see that in a moment here. And then we've got some statistics, the number of files that were written, the number of rows that were written, how many bytes it took. And then right down here, this is where it says add. This is what I typically call the Delta context. So this is, but you could more appropriately call this, this is the Delta at that specific, or the Delta table at that specific version. We have added this particular path. Now there's some stats on here. There's some the size of this table. But the important part is this path. And I'll show you why. Going back to the actual table here, let's scroll down. You'll see right here in this statement that I've got, it's saying select star from Parquet, tables, dim customer, blah, 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 blah. The whole point is that I've got a key here. Let's look at 77D. You'll notice here, 77D. So this is the actual file that I'm looking at in this instance. So when I query that file, what's returned is everything that was in that initial insert statement. Pretty easy. The next thing that takes place is I do an update. So I updated where my ID equals 1. So that's the Jarid record that's in there. And I set the salary to 150K. If I go down to this particular record down here, you'll see we've got 150K associated with the Jarid record. Notice that this is reading an entirely different file. Again, let's look at for the file 50E. Going back here, we'll look at our Delta log. We'll go to number 2. And let's see what happens in here. So you can see there was an update that happened. There's some predicate information. There are some efficiencies that can be created with update predicates or delete vectors. Those are more complicated than what I wanted to get into within this talk, but it absolutely exists within there. What's particularly important is down here. We have 2 areas now. There's a remove and there's an add. Remember on the add, we had this 50E, and down here we are removing 77D. So when I query the data set, it returns all the records within just this one file. That's what happens on an update. Let me just go to, I just have a drawing here that I like to use. Bear with me one second. I'm going to switch screens so that I can draw on this this a little bit easier here.
While you're switching screens,
I'm just switching screens. Yeah, sorry.
A new question is coming in. So one of the attendees is asking, so every time we do a transaction, a new Parquet file is created?
In general, yes. So you have a new Parquet file that gets created for every time that you do a new transaction there. So let's go. So here's kind of my drawing. On the left-hand side, we have files. So these are the files that actually get stored. And then on the right-hand side is like the Delta state at that version. So the initial create doesn't actually read a file. So let's ignore that one for now. We have, let's go, we have transaction number 1. So the transaction log, we have a number 1 in there. When we query that file, it's going to go and say, that's in my my Delta state at that version. When we update the record, what ends up happening is this is no longer in context. I then have a new value in there, or a new file in there. That is my row 2. It's a completely separate Delta Parquet file. Let's go and take a look at this third one. I'm not going to go too deep into this because you'll probably kind of see where this is going from here. The next one that we have is a delete operation that happens. So we're deleting that second record from this column. We're deleting Mike from our data set there. So this goes back over here. So this is a file that still exists, but it's not in context anymore. There's another file that gets created, this number 3, that only has 1 record in it. You're probably going to start seeing some implications of this, is that we are starting to get a lot of data duplication, and there's a lot of these small files that tend to be overlapping, if you will. So let's do another operation in here. Hopefully that all right. I might have to restart this momentarily, but that's okay. I'm doing this operation down here. So this is my next insert, if you will. So I'm inserting the Brad Pitt record, who makes $1 million, probably more than that, into our data set. Let's go look at the the Delta log that happens in this instance.
Jared,
Yeah,
we have another question coming in. Actually, it's a good
absolutely.
one. So the question is the info from the Delta Parquet file also used for operational purposes? So if we get a bit more specific regarding the action, for example, append, delete, which the key value of the record, is that used for auditing purposes as well?
Sorry. I'm just trying to reread this. So regard. I apologize. Which question are we referring to? Is it the one from Roger, where is his info used for operational purposes, or?
Yeah, exactly. And then it just
Okay.
continues below it slightly more information.
Oh, absolutely. Regarding the action append delete, which key value meant for auditing. So this is all used for time travel, and this is so that we can have ACID compliance. So I could have somebody querying my data set. Let's go back to the drawing here. If I have, say, my current version is at version 2, right? I could have somebody go in there and say, select star from dim customers. It's going to go and start looking at this second file that's in there. That's going to have the 2 records with the update that happened. Concurrently, at the exact same time that person is reading the data, I might have something that somebody that goes in and say, actually, delete this record. It's not supposed to be in there. This doesn't fail because the reader was still reading this version. Even though we updated our information to say that the 3rd record is now the one that is in context, that original one is generally what's in there. I can still time travel and go back and forth, which again, I will show in a moment here to say, you can do this. You can query your data at a specific point in time or as of a specific version. So if you need to do some auditing or traceability, you have the full ability to do that. That answer your question? Somebody was asking, aren't Parquet files memory intensive? They can be memory intensive, but in general, because they're highly efficient and the types of queries that we're doing on them, they are really, really good for most use cases. Again, you want to make sure that when you're using these, you're using them because you're doing those analytical operations. I'm aggregating and I'm filtering. You can also extend that to a lot of ML applications, but those really extend to aggregating and filtering. Okay. Let's see here. This is my 4th one. So this is after I did that insert operation. So in here, let's go. We've got a write operation. And down here, you'll notice that I have an add. But unlike the last time where we did our first update and we did the delete, there isn't actually a remove operation that takes place in here. So I'm not removing a file from the Delta context. What I did here is I added this file with the key of 879 into context. So if I go back to my drawing here, what I've done essentially is I've created another file. This is transaction 4, where both of these files are in context. All right. So let's go back to the actual Delta table here. So if I were to do this select statement, this is the one I just did, you'll notice that I have both these records in there. Here's the Jared record, that's row number 1, and the Brad record on row number 2. These are actually in 2 separate Parquet files, and I can prove it by looking down here. The one file that I had was this 55A, and the other one was this 879. So let me just comment these out for a second here. Execute that. So this is going to give me just my first record. This is going to be the Jared record. So Jared is stored in this Parquet file. if I were to comment that out, I'll uncomment that one. Oh, not the union. I'll uncomment that one, execute this one more time. Now it's going to return the Brad record. So what the Delta log is, it really stores what files are relevant at that moment in time. Okay. Let's take a break, take a look. Okay, no questions at this point.
I have a question, Jared.
Yeah,
I didn't
go
put
for
it in
it.
the chat window, but actually it's something, yeah, it isn't in there. So I'm just going to ask it straight away. What if, since we were talking about the operational purposes and auditing, what happens if you execute the vacuuming process later on?
We're going to get there. I have that
Okay.
as part of this demo. So
Great.
I will get there, I promise. All right. Let's go into, I'm going to execute this operation here. This just inserts, 6 or 7 more transactions. Each one of these executes one after the other, not concurrently. If I did this concurrently, things would fail. But you're going to see as soon as this cell is finished completing, I'm going to have what we were at transaction log 4. So this is going to be 5, 6, 7, 8, 9, 10. There's going to be 10 transactions within our Delta log at that point in time. And so let's go over to the Delta log. I have to refresh this here, and you'll see that there's going to be 10 operations in there now. Importantly, I get this checkpoint Parquet. If I were to go look at this last one, you'll notice that, again, this is just all this is a write operation and an add. It added an additional Parquet file to the Delta context that I'm looking at that particular moment in time. If I go to my drawing, what this is going to be is basically we're going to have 5. There's going to be, a bunch of files in here, and then ultimately there's going to be transaction 10. So all of these are now in context. So in order to query my table at this point in time, I have to read, what's this? 6, 7, 8 different files in order to understand what's going on. I could also look at this file in particular. So let's just quickly copy that. And I'll go over here. I'm just going to show again that if I query this particular file, it's going to be one of the files that I looked at. This is going to be IDs number 14 and 15 right there. So as soon as this pops up for me, you'll see we have IDs number 14 and 15. Okay, it's a completely separate file than all the other ones that I looked at. Okay, let's look at optimizing. Optimizing is one of the most important things you can do to your system in order for performance and for compression. So I'm going to do this optimize function. Oh, I apologize. Before I get to there, I mentioned this but didn't address it in any way, shape, or form, which I meant to. Checkpoints. What a checkpoint is it basically every 10 transactions that happen within a Delta table, a checkpoint is created of the files that are in context at that point in time. We're also going to have this last checkpoint file. So in order for me to get to where I am or where I need to be within the Delta log, if I needed to go to, the 1,000th transaction, I might actually have to go and read, 1,000 different of these JSON files in order to know what the context needs to look at that point in time. A checkpoint means that all I have to do is read the last checkpoint. All this does is point back to what the most recent checkpoint file is, and then it will save just 10 transactions. So the most number of files that I'm going to need to read in order to get the state that I'm in is 12. I need to read the last checkpoint. That points to the checkpoint file, and if 10 transactions happened after that, I'm going to have 10 files. or 10 JSON files that I need to read. That's what checkpoints are for. So if you have thousands and thousands of transactions, which you ultimately will, you don't need to read thousands of Delta log files in order to get the information that you want for that moment in time. Okay. Any questions on that? Is checkpointing kind of make sense?
Currently, no questions.
Perfect. Let's look at optimizing. I'm going to optimize this right now. I'm going to execute that there. What optimizing does is it takes all the data that is in those disparate files. So you saw that I had, a couple of different files. I think I had like 8 or 9 in my my little field there. What it's going to do is it's going to take all of these files, put those back into my Delta log, and then write me a single file with all the information in that log at that point in time. So as soon as this finishes, we'll go back to our table here. I'm going to refresh this because it doesn't refresh automatically. I'm going to have an 11th transaction here. So let's click on that and see what happens in here. You'll see this is an optimize command. A bunch of stuff. We have data that's being added and removed, bytes that are removed and bytes that are written. There's one file that gets added right here. Let me just copy that because I'm going to need that for a second here. And then it removes a bunch of different files. So remove. All of these down here are removing files in the Delta context at that point in time. So if I go back to back here and I query this one Delta file, it's going to contain the state of my data at that moment in time, all within one file. And it'll, benefit from all the compression and other bits and baubles that the Parquet file has at that point in time. So all this data is in one file, not 8.
Jared, we have a question coming in about the checkpoint file. Is a checkpoint bigger on disk than on Parquet?
So checkpointing doesn't has nothing to do with Parquet. Checkpointing is only with Delta. Delta basically says at this checkpoint, these are the Parquet files that you need to read in order to get your data at that state. That answer question? We good? If you need follow-up, let me know. Yeah, the checkpoint is part of Delta, not Parquet. Parquet is the file format. Delta is how we know which files to read at that point in time. What's nice is that all of this allows us to do that auditing actions that I was talking about prior. So if I want to describe my history, you'll see in here, I've got a bunch of different versions that take place. Let's zoom in. I'm going to zoom in here and be able to scroll around as well. So this first thing that happened was a create or replace operation on that table. Let's get rid of that. I don't actually want that highlighted. So there was a create. This is the first thing that I did. The second transaction I inserted a file into there. I updated a record. I then deleted a record, and then I wrote a bunch of different things. And then the last thing I did was optimize. So each of these gives me a specific Delta version that I could query my data as of. I could say, give me the data as of version 7, and it's going to describe what's actually important at that moment in time. I'm saying version because it's easier for me to demo this by querying the version, but you can also say, give me the data as of this timestamp. So as of yesterday morning, before my ETL ran, give me what the data looked like. So again, those are for your auditing purposes. So if you have a whole bunch of operations that happen as part of your ETL processes, it can just give you as of a specific timestamp rather than trying to search through the Delta history and find the specific version that you wanted to look at that point in time. Let's take a look at this. This is time travel. This is exactly what I was just trying to describe there. This is saying, that's going to be executing. There we go. This is saying that as of version 7, so I showed the Delta history table for a moment there. As of version 7, what did my data look like? And it's exactly what's in this table down here. There are only, what's this, 8 records? There's only 8 records in my table at that point in time, versus I know the table actually has 14 records for the transaction number 11 that I'm at this point in time. So this is how time travel ends up taking place. Jarmo is asking, is optimization something that Fabric automatically does, or should you regularly apply the optimization procedure depending on how quickly the parquets become sparse? Really, really good question. Really, really important question. I apologize. I cannot remember whether optimization happens automatically or whether this is something that's still on the backlog. I know it was on the backlog when I was first writing this presentation, but it may be automatically happening on there. I would have to do some research and get back to you.
There was another question as well, Jared. But
Oh,
I actually think you mentioned it just before the question was asked. Like, can you quickly describe the difference between Parquet files and Delta files?
Absolutely, yeah. So just addressing that, Parquet files is the specific file format that the data appears on disk. Delta is the way in which you need to read different Parquet files. You could have data repeated multiple times between different Parquet files, and you can append Parquet files together in order to read them. Delta allows you to select the Parquet files that represent your data at that particular moment in time. Parquet stores those files on disk. Hopefully that addresses the question.
Yep. In the meanwhile, another question came in as well, and I actually love the question.
This is a great question. This is the one that this is the one that I'm really like addressing, because does this mean you don't have to implement slowly changing the dimensions type 2 within dim tables anymore because of time travels? No. You still have to implement slowly changing dimensions if that's something you need to use. I would argue for the vast majority of use cases, you don't need to implement slowly changing dimension type 2 for business, general business analysts. I will argue this till I'm blue in the face. For specific use cases, you absolutely need to implement slowly changing dimension type 2. But I'm going to show you where this whole process breaks right now. And that's when we talk about vacuuming. So we're going to implement a couple of different vacuum operations right here. So let's look at this one right there. So this is, I'm going to do a dry run. And what a dry run does is it basically just tells you what's going to take place when you vacuum this table now. When I say retain 0 hours, it basically says get rid of all history. So you'll probably see where that's going when I'm addressing Roger's question right there. So this is going to throw an error because there is a fault, or there is an option that automatically says you probably want to store more than 0 hours of retention at this point in time. So be very, very, very careful. Let's go out and change that operation. Get past the error log. Here's the option that I can set. So I'm going to set that duration check to false. So now I can delete whatever I want. And now let's actually execute this operation down here. So we're going to, this is going to be an actual vacuum of the tables in there. What dry run does is basically just shows the files that would actually take place in that. Sorry, I'm zoomed in and now it's okay. So here is my file path. So it vacuumed that table, retaining 0 history. If I go into the Delta log here, And let's just refresh the table. And I'll refresh this. You'll see that all my Delta log information is still here. I can still look at all this. I'm still at transaction number 11 in here, and I can still query that. But let's look at the actual customer files. Oh, let's refresh. Damn, customer refresh. There we go. Refresh. Hold on, I did something, or I didn't do something. I apologize. I executed the dry run where it said what files are going to be deleted, not actually deleting them. So when you do a dry run, it just tells you what files are going to be deleted. So let's actually execute this. A dry run is not going to cause any sort of Delta transaction to take place, so we don't need to do anything there. Just take a second to actually execute there. And now let's go back. Going back into the Delta log for a moment here. A vacuum operation actually causes two transactions, one at the start of the transaction, one at the end. And I know I'm at time here. I apologize. I have one more thing I want to show, and it's probably my favorite thing for development purposes. So if you're a developer, definitely stick around for another 3 minutes. I promise I'll be very quick there. So transaction 12 is the start of the vacuum. Transaction 13 is the end of the vacuum. Dim customer, you'll notice there is a single Parquet file. This means they got rid of all my Delta history. So I can no longer time travel. It's going to cause anytime I do a select star from this table version as of 7, it can't find those files anymore. So the files are still referenced within the Delta log, but the files do not exist on disk. This is why you still have to implement proper slowly changing type 2 dimensions, unfortunately. All right, so that's the error. My favorite part of all this, and really important for anybody who is developing this type of thing, is the idea of shallow clones. You'll see right here, I have a shallow clone. I'm just going to very quickly execute this, and then I'm going to show you what this table actually is. I have a complete copy of the dim customer table. I can query this table. You'll see I'm not going to execute this because I don't need to. I have all the data that is in there, but if we look at the Delta log, let's go in here. I'm going to refresh this. You'll see there's should be a dim customer copy table right here. If I view the files associated with this, what this is going to show is that there are no Parquet files in here, and the Delta log that exists points to the other table that I was playing with before. This is so useful because now I can do proper testing on production quality data for ETL purposes and not create physical copies of that data. I can run my ETL on my production data without affecting any production data. I use this all the time in proper ETL tests. This allows us to do actual test-driven development within analytics. By hands down, my favorite feature of Delta Parquets is that shallow copying. So anyways, I know I've gone over time. I don't want to impede anybody's evening. So I want to thank you all so very much for coming. It looks like there's one question in there. In which cases would we use the deep clone then? Deep clone I use for archiving. So if I need to archive a file off, use a deep clone, put it into some Delta Lake that's probably not in Fabric. Great for archiving purposes. All right. And I'll stick around for another couple of minutes. If anybody has questions or wants to come off mute, I'm good for that.
There is a question coming in. in which use cases should we use deep clone then?
Oh, that's the one I was just addressing. So that deep clone is for more archiving purposes,
Okay.
if you want to. That takes a physical copy of the Parquet files and the Delta table at that point in time.